Yeah, so we were discussing about the Gauss law of accidental errors, where we discussed about the accidental or random errors. They follow the Gauss law of accidental errors, and we have very simple three axioms. That is, small errors are more frequent than large errors. Positive and negative errors are equally likely, and very large errors do not occur at all. So that's how we, I mean, in case of our understanding from the basics, that after removing the systematic and gross error, the only error remains, which is random error, and that follows the Gauss law. The beauty is that we have certain background in terms of Gauss laws, then which we try to apply and try to see what type of distribution we have to solve our problems. Again, with this slide, what we are trying to present here is that for large number of observation with the very small interval, the histogram tends to be smooth. That is a bell-shaped curve, which is symmetric about the mean of the error, which is 0. Now here, what we are trying to represent as that that here we understand from our conceptual understanding that we want the random errors to be 0. Obviously that would be represented by the mean of their random error, that would be 0. So obviously the mu e would be 0. So whatever the bell-shaped distribution would be presented, it would be presented around mu e is equal to 0. Mu e is equal to 0. Okay, so that is one of our discussion part that held yesterday in the previous class. The Gaussian PDF for random errors using normal equation, it can be written in the similar fashion that you could see. We want mu e to be 0. If I try to if you try to understand the equation from our basic PDF, the fx is equal to 1 upon sigma root 2 pi exponential minus 1 by 2 x minus mu by sigma square. So here, if we represent x, that is random variable, as random error, obviously the mu would be nothing but the mean of random error, that would become 0. So the equation becomes this. It's very simple. It's nothing new which we are showing. It's very simple. So the e, which we call it random error, representing the argument of this PDF whose mean value is 0, and obviously this error, which is abscissa of the probability curve, and this we apply as expectation, which is what is expected from this random error is that it should be 0. Obviously this curve, the ordinate would be f function of, I don't know what happened to this. Yeah, it's a little bit. Okay, so that would be the ordinate of the curve. The h, which is the parameter describing the shape of the probability curve and can be considered as the precision index. Okay, so that is one thing which we need to see. What is h? H is nothing but, you could see what is replaced here. It is replaced. What we have replaced? We have replaced 1 by sigma root 2. Okay, that we have replaced and represented as h. So related to the height of the peak of the curve, which occurs at e is equal to 0, we'll get h by root pi. So also related to the abscissa of the point, which is related to the point of inflection. And similarly, that what we have done in the case previously, we obtained the second derivative first, and that the equation which, when it becomes to 0, will get the point of inflection. Okay, so this is the basics of your Gaussian law of accidental errors. From that, we understood how the error would behave if they have to follow certain probability distribution. Please remember, we have discussed two cases. In first, we apply the normal distribution curve to observation directly, isn't it? In the first case, which we discussed in previous two classes, we applied the normal distribution to the observation itself. But in the second case today, what we are doing, we are applying the similar kind of bell-shaped curve to the error part. That's why you see we replaced x as e. So this is the two thing that you should not mix the two. This is the part where we are trying to see whether what is the behavior of the error which we are describing. Okay. So characteristic of a Gaussian curve of errors. This is all we have discussed. They have to follow all those basics which we have discussed before. One is the bell-shaped curve, symmetric about e is equal to 0, maximum value of ordinate at is equal to 0 at with value equal to h by root pi, asymptotic to axis e axis at plus minus infinity. As PDF, it should satisfy the following condition, which was the same. If you recall what we have written in the case of observation, minus infinity to infinity fx dx. That's how we have written, isn't it? Similarly, we have written the corresponding cumulative distribution function also. But here, let us just repeat the fx value here. So we have replaced the value here. So that's how we are replacing it. That implies that area below the curve fx is unity. So by differentiating the above equation, we can always show what we have just written here, that um, uh, the the point of inflection would occur at abscissa e is equal to plus minus 1 by h root 2. So this is all simple uh, uh, basics which we have to follow. There is nothing new which we have already discussed from the previous content. Okay, so here we are representing again similar the relationship. See, there is one thing which you need to understand. It is also error, and we are relating with another term which is very popular in our geoinformatics domain. What is the standard error? Whenever you write any content, whenever you try to work with any data, people will always ask you what is the error in your data. So that error has to be represented in a certain technical terms, isn't it? You cannot simply say it is error. The people will ask what is it is error. If it is a systematic error, it is a random error, or it is a gross error, then you categorize it with, let's say, that error as random error. Then in random error also there are several categories. So we are just basically focusing on right now as a standard error that is very popular in terms of communicating, and in fact many standards have been made over this standard error. So what we are doing, we are finding the relationship of e, small e, let's say, with standard error. So here you know that error is nothing but the deviation of individual observation, isn't it? So what we are doing, we are trying to see that error in terms of your so-called variation in the individual observation with the most probable value, isn't it? So sum of squares of the errors when divided by the total number, that represented by the square that represented by the term called standard error, and in the standard deviation is widely known as standard error in geoinformatics literature. If you follow any book, and is defined as the positive square root of the arithmetic mean of the sum of the square of the errors. This is the very basic definition which you have seen at multiple places, probably by your in 10th standard, maybe 9th standard, you have seen this kind of definition. That is also sometimes called as RMS error, which we call it root mean square error. So in case of continuous random variable, it is defined as this. This is very popular equation, which you have to remember it for quite some time, because when we discuss about the error propagation, we will start from this very basic. Okay, so the standard error, which is defined as sigma, its variance is defined as the sigma square. And in the case of sigma square, you could see how it is written. We are writing the error square as well as multiplied it with the probability distribution. Now this is very important. You try to understand what we are what we are trying to understand that part as we are writing the error variance part as uh, nothing but the integral that sum of square term multiplied by the probability distribution. This is very important point, that how that's how you represent in terms of your probability distribution, how you are representing the variance. Then subsequently we are substituting the function. What is our function of error is h by root pi. Uh, that is we have written in the previous slide also, h by root pi exponential minus e square by h square, and we are when we replace it in the above equation, that becomes this. It's very simple equation, sigma square minus infinity to infinity e square fxe, and then fxe is present. Now why we are deriving? Now overall objective is, why is so much derivation involved here? What we are achieving, isn't it? Because it is good that I mean, we can follow the mathematics part from books also, but what we are trying to represent here, we are trying to go from this part of understanding towards a development of, or a discussion on a very important principle, which we call it least square principle. So that the basics start right from here, because we in least square principle, what we are doing, we are trying to minimize the sum of squares of the residual. If you are involved with the least square understanding in somewhere in your previous education, that the definition itself says least squares. But what are the least in that part? It is the sum of the squares of the residual, okay, that are going to be minimized, that are going to be found as least. So with that understanding as our milestone to achieve that, this is the basic derivation which we need to see. Okay, anyways, I hope you are following it. So it is again from minus infinity to infinity e square h by root pi, and obviously the equations which we have written, minus h square e square. Okay, so evaluating this integral, which we will ultimately give the standard error in terms of precision index, and you will get sigma as 1 by h root 2, which we in fact we have seen in the previous one also. Okay, again our since in geoinformatics literature, it is not possible that every time you have only have to work with single variable. Instead, a problem would occur where you have to work with multiple variables at the same time. So obviously we need to go from single dimension to multiple dimension. Any problem, if you talk about your geoinformatics domain, no problem is there in our field which is a single dimension. Now it has become multiple dimension. In fact, you could correlate with the multi-objective optimization also. In a multi-objective optimization, you have to optimize so many variables at the same time which are affecting the cost of the function, isn't it? If that is the case, then you have to work with a multiple objective. Similarly here in our domain, we do not have to work with a single variable. In fact, we have to work with multiple variables, and in fact the variable and the parameter, they both are in multiple dimension. Okay, for example, if I just explain that linear and angular measurement both occur at the same time, so that is already another two dimension which we are talking about. Okay, so based on Gauss law, or our normal law, the PDF is written like this is very popular. You are very much familiar with this now. I just again request you to follow and practice a lot more compared to just looking at those slides and looking in your book. You have to write it down from your hands. That would much more comfortable for you. So what is the probability distribution? We again know that 1 upon sigma root 2 pi exponential minus x minus mu upon minus 1 by 2 1 x minus mu by sigma square. But for n dimension, what we are trying to see here, that's very important to focus it here. We are replacing sigma with this. We are replacing sigma with this, and we are rewriting this. Okay, isn't it? This is what we are doing. If you try to see what we are doing here, we are representing the sigma by mod of sigma x, capital sigma I would write here, and this term is rewritten here. Now what is it? It's very simple. If you just follow me for quite some time, then you will understand this part. We are writing here as, since we have to convert it for n dimension, the problem as we have discussed, it should be explained in terms of n dimension. Then what we'll have to do, we'll have to see that we have to write the so-called the function x, again the probability distribution function, 1 upon sigma root 2 pi. So initially it was 1 by 2, now it has become n by 2. Okay, Hopefully very much clear. Then the sigma is called standard deviation if you consider only single observation at a moment, okay? Or length of the table measured for 100 times if you follow like that. So if it is measured for 100 times, you can have a standard error, okay? But if you have multiple observation or multiple variation which you have to take into account, you cannot work with a single dimension. Instead you have to consider all possible dimension. So here comes the square root, because obviously sigma is the square root of the sum of the errors, and that's why we have written it as a square root of positive. Mod represent the positive because we have to take the positive out of that box, and the sigma x represent the VCV, which we call it as variance covariance matrix. Okay, we'll discuss more about VCV, but you just have to understand that it arrives from the VCV. Now what happens in the case when you have to work with multiple dimension, what is generally the root cause to go ahead with this is because you are not only working with one sigma. Instead you have to work with 2 sigma, you have to work with third sigma, you have to work with 4 sigma, and so on. It is not only you have to work with length, you have to length, width, height, and whatever parameters are there in a single set of observation, you have to work with all that. So sometimes what happen, generally in geoinformatics, it is possible that some two observations are not correlated with each other, but sometimes it happens that your observations are correlated with each other. And then if the correlation happens, you will have the covariance factor also, like sigma 1 square, sigma 1 2, sigma 1 3, sigma 1 4, like that. Okay, so this whole set of values which we are writing, that becomes your variance covariance matrix. Please remember, the diagonal part are known as variances, the non-diagonal part are known as covariances. And the same matrix we are trying to use it here, subject to obviously our understanding is that all these observations are non-correlated, so the non-diagonal part becomes 0. And then
Hello, sir. You are not audible.
So I hope now the voice is audible, Sumit.
Yes, sir, it is audible.
Okay, due to some network issue, it got disconnected. Okay, so we were discussing about the n-dimensional nature. Then the second part, which is our point of attraction here, is how do we write this the x minus mu square if we have to consider multiple dimension or a multiple vector. So here they have written like that. Initially they have written x minus mu x, and that is as a transpose, and then sigma x inverse, or and then x minus mu x. So if you try to follow from your matrix principle, if anything has to be written in terms of a square, you write as a transpose, isn't it? Isn't it? You follow like that, and then one could also argue that a transpose a is also another way of writing. So how do we choose from which one we have to follow? It is generally chosen in a sense that how do we want to be represented in terms of our data set? How do we want to represent our data set, isn't it? So if you follow from your basic single dimension problem, you want to write like that: exponentially minus 1 by 2 h1 square plus h2 square plus h3 square, isn't it? So it is coming at as one cross n kind of thing, isn't it? It is coming as 1 cross n. So that's why the transpose is initially taken, because your data set is vector is like n cross n. Your observation are always n cross n. So if you multiply n cross 1 to 1 cross n, the multiplication of two matrices like this, n cross 1 to 1 cross n, it would become ultimately the n cross n. If you follow your basic mathematics, if you multiply two matrices like n cross 1 to 1 cross n, it would become n cross n. But what we want our final output as 1 cross 1. That's why we are writing 1 cross n, that means transpose first, then the individual matrix. So that's why we are writing like that. It's very basic difference, but sometimes what happens, students may get confused. How do we want to write the transpose kind of, because in future when we go ahead in this course, we'll see many a times you have to write the function in terms of its some transpose, in terms of variety of things, isn't it? But what is our objective? Our objective is to first understand how do we want to write the function in terms of matrix representation. So there is a shortcut which I have adopted, and I also communicate to our students, that first you try to see if it is a single dimension problem, how do you want to write the solution. Okay, so if you, and how do you want to be represented in terms of final output? So you want your final output like this, isn't it? That 1 upon exponential minus 1 by 2 h1 square plus h2 square plus h3 square, like that, isn't it? Or sigma square e1 square plus e2 square plus e3 square, like that. So when you write a transpose, you cannot achieve it, so I have to go for a transpose a. Okay, so that's why the transpose comes first, then 1 upon sigma square. If you follow the matrix inverse principle, 1 upon sigma square is in one dimension. Inverse of a matrix is represented in terms of n dimension. So that is represented here as x minus mu x, sigma x inverse x minus mu x. So this is the way you write for n dimensional case, the normal curve. Secondary, your vector x is like this. As I said, it is a transpose. Please follow. This is a transpose of x, isn't it? It is not x. X would be x1, x2, x3, x3, like that. Okay. So determinant is your mod of sigma x, which is your variance trace matrix. You please follow uh, from your basics that it is the square of Mahalanobis distance, which is very popular indicator, and in fact it is an Indian who has written this. So the Mahalanobis distance, if you remove this this sigma inverse from here, it would be go and become Euclidean distance. If you just remove that sigma inverse from here, it would become Euclidean distance, x minus mu x transpose x minus mu x. That would become the Mahalanobis distance. Okay, I hope you are following it. If you remove that sigma inverse, but uh, first comes the Euclidean distance, then comes the Mahalanobis distance, and the reason for coming the Mahalanobis distance is simple, that variance has to be accounted while calculating such kind of measurements. Okay, so this is one. Any question in this? You can ask. If you do not have any question, we can move ahead. So next, our objective is to understand the quality of the observation. Okay, as we discussed in the laboratory class, the quality of the observation is expressed in two terms. One is your obviously the accuracy, and another is precision, as we discussed yesterday. So as accuracy is nothing but indicates nearness of measurements of measured value m to true value. Okay, so yesterday also we discussed the accuracy is closeness. The closeness term comes to true value, and in the case of precision, it is nothing but the closeness to observations, closeness among observation. Okay, so in the case of accuracy, we define it as nearness or closeness of measurement uh, of measured value m to true value, or the closeness with respect to the true value. And true value is always unknown. That is the one understanding which we have learned from our few basic previous lectures, that true value is not known. What we have the estimate of the true value. So therefore the accuracy is indeterminate in practice, and we resort to other method of accessing the reliability of measurement to decide which of the measurement is best, provided we have decided what is best. It's very good line. It's very critical lines of our geoinformatics adjustment computation, that we do not know the true value, obviously, because the nature of the observation is such that the accuracy is indeterminate in practice. We cannot comment always about the accuracy, or we generally do not make a statement about the accuracy. Accuracy is a very vague word. Okay, we resort to other methods. What are those methods? We'll discuss, of accessing the reliability of the observation. Okay, to decide which of the measurement is best, provided we have decided what is best. In fact, provided what is decided is the best, is mean which is the indicator of the true value we have chosen. This is what we are deciding from here. Okay, so another term is precision. Precision is which is allow us to make such judgment, and refers to the degree of consistency between measurement, and is based on the size of discrepancies in the data set. We generally have this understanding that precision is measured as a closeness among observation, how well we are repeating our observation, isn't it? Because we have discussed that we should have redundant observation, but how well we are repeating it, it's also a very good indicator. So that is the indicator of precision, and it helps in two ways. One is it is an indication of the spread of the data set, how your data set has spread like this. So highly precise, nearly precise, less precise. So very much precise because the peak is there. The data set is very much around the mean of the observation. Okay. So it shows that it is an indication of the spread of the measured value of quantity. Several values grouped closely together are said to be more precise set of measurement than any other broader spread of values. And this this precision is inversely proportional to variance. Now we are calling precision as inversely proportional to variance. This is what we are saying. This is precision. We are saying that if the deviation is less, what is the variance? Variance or standard deviation are the measure of the spreadness. So we are saying if the spread is less, obviously the precision would be more. I hope it is very much clear. What is the spread? Spread is nothing but how do we represent the standard deviation and the so-called variance. Variance, if this is the mean line, if this is the mean line, the deviation, this is the deviation of the data set. If this is the mean, if this is the deviation is represented by sigma. If deviation is less, the data is high precise. If deviation is more, that means data is less precise. This is what I meant. If you have any confusion in this, it's very basic concept. You should be remembering all time. Denote something to higher manufacturing standard. It is an indication of uniformity or reproducibility of the result. You know, if you are capable enough of reproducing your measurements. Without a high degree of precision, the blunder may go undetected and uncorrected. Why? Because if your data set is already having a large sigma value, how come an outlier would be detected? You would consider this outlier would as a part of your measurement, isn't it? This is highly likely that if you do not have precision in your measurements, you would choose one of the measurement that have higher sigma as part of your observation, and you would have garbage in your data set that would move. The analysis of precision can be misleading if a certain degree of precision is implied but not actually attained. To obtain higher degree of precision, it may be necessary to use more sophisticated instrument or equipment or more time consuming methodology. Okay, so there is a very good paper on accuracy and precision which you can download it. It's by Wang. It's very much about how accuracy and precision are related and how well at what time we have to choose what indicators. Okay, but at present you should have to form your basics. Okay. Okay, this is the one example which is very popular but has to be understood properly. So we have four cases. Okay, we have four cases. One is called as A, another is B, C, and D. So in the case of A, you have four observation: one here, one here, one here, and one here. Okay. In case of B, you have all set of observation here. In C, you have all observation here. In D, you have observation here. Okay. So I'm just deleting this part so that you could properly see. So in the case of A, you could already understand that A is not accurate, but A is accurate but not precise. Why? Because the precision is about the closeness among observation. Okay, precision is about closeness among observation, and your accuracy is nearest to the true value. So these four observation, they are very well separated out. There is only one observation which is near to true value, but obviously these four cases also do not represent the accuracy. Only because of this we are just saying that A is partly accurate. I would say I would not use full accurate, I would use accurate and not precise. In the case of B, it is neither precise nor accurate because no value is near to the true value. And in the case of C, it is very close observation, but on the left hand side, top left hand side, so they would be considered as precise, but not as uh, accurate. Similarly, in the last case, this is a very real world ideal world kind of scenario that the data is accurate as well as precise. So obviously, the reason why tend is always seen in that direction. In the case of C, it may be caused by the bias, that is systematic error is present in the data set. That's why a deviation, a slight single pointed deviation is seen in the observation. That's why we are calling it as this is caused by systematic errors. Okay. Similarly, in the case of D, which we call it as accurate and precise, it is desirable for data collection. Okay, so in the case of B, you could see such kind of data set you never want, that you are neither near to true value, neither you are precise, you are just collecting data and it is useless. So it is assumed poor. Okay, you should avoid it. Okay, so this is the one slight example of your understanding for your so-called precision and accuracy. If you have any question regarding this, you can ask. Feel free to ask any question. If you have any some silly doubts also, that is also not a problem. You just properly understand the sort of I mean our understanding towards precision and accuracy. So moving ahead, we have measures based on Gaussian law. There should be certain measures of existing random error associated with each estimated value to be described or expressed as the degree of its goodness, reliability, and repeatability. You know, every time we go ahead for measurement, what we want is that our measurement has to be precise. Okay, and that's why we always want that the precision should be maintained so that you could reproduce those observations, reproduce the similar kind of result in multiple scenarios. So that's why we have to measure certain the so-called degree in terms of its goodness, in terms of how much reliable is your data set. Sometimes every time people ask how much reliable is your data set. So reliability could also be given in terms of certain indicator. Okay, so these question of goodness of the data set, reliability of the data set, repeatability of the data set, these are always asked. Okay, so this measure should help in accepting and rejecting certain observation, and depending on the criteria that has been decided to meet. Okay, so the measure of errors is essential to compare different set of measurement and hence accepting the more precise one. So in practice, beside the word precision, one always hear the other two word which we call it accuracy and uncertainty. Uncertainty is the word you will only hear in our engineering domain, where you have the opportunity to collect much more data set, or you have to work with much more data set. Then obviously people ask about what is the uncertainty associated with a particular results. Okay, so it's very basic understanding. So uncertainty, if we move ahead with the term uncertainty, so in addition to precision and accuracy, uncertainty is another term frequently used to express reliability of the measurement. Please remember, in the case of reliability, you have to measure it with the uncertainty. How much uncertain about your data set being a certain value within this and this. Okay, the certainty always work with the range. Okay, so you cannot work with a single value. You cannot work with a single value. You have to work with a range. So it is the range or interval within which it is expected that the errors of measurement will fall, of course, with a certain prescribed probability level. It's a very important line. Very important line. You should just read it very carefully. This one, because ultimately this is the I mean statement which we are going to follow if in multiple examples. Okay, so again, I'm saying as uncertainty cannot be a single value because you are not, if you are not certain, obviously you cannot be certain of a particular value. You have to be certain. You have uncertainty zone where it is expected that your observation will fall. So that's the same line is written here. It is the range or interval within which it is expected that your errors of measurement will fall. obviously with a certain degree of probability level. अब आप you could also see that how the statements will be formed. What is the 90% with 90% probability? Tell me how your observation will fall with respect to the mean. What is that with 95% probability? Tell me where your observation fall with respect to mean. So you will answer in repeat of a statement that with 90% probability my observation will fall between mu plus minus this sigma. Okay, obviously the sigma will play here support role to give the answer of uncertainty. Okay, uncertainty you are getting with the help of sigma. But since you have to represent it with a range, sigma will help you to decide that range. You get it point? You get the point? So this is equivalent to the word confidence level with alpha probability. Okay. For normally distributed observation, it is expressed in reference to the standard deviation of measurement, which I just mentioned. That you have to tell us in terms of standard deviation of the measurement. Okay, any question? Very strong line is this. You have to understand this part, because based on this we'll try to attempt certain problem.
Sir,
Yes.
can we apply this uncertainty concept in standard normal distribution, sir, where mu is 0 and standard deviation is value 1?
Sorry, I couldn't understand your question.
So can we apply this uncertainty concept in standard normal distribution, where
Obviously,
mean is 0
we
and
are working. Yeah, we are working in that random error scenario, which is following the Gaussian law of distribution. We are applying to that only.
so can we say, sir, the range in between -1 and +1?
-1 + 1, -2 + 2, -3 + 3, -4 + 4. Every type of range we have to cover in with the help of your sigma.
Yes, sir.
What specifically you want to ask?
So actually in standard normal deviation, sigma value is 1, sigma square. Then can we say the range mu minus sigma and mu plus sigma? So can we say the range of uncertainty is -1 to +1?
Now I understand your question. No, see,
Yes, sir. Yes.
standard normal distribution is a helping hand. Okay. See, standard normal distribution is just a helping hand to you, so that you could easily compute what you want. स्टैंडर्ड नॉर्मल डिस्ट्रीब्यूशन कोई आसमान से नहीं उतरा है. आपने कंप्यूटेशनल एफर्ट्स को इजी करने के लिए एक अल्टरनेटिव ढूंढा है कि हम कैसे टेबल वगैरह देख करके आंसर बता दें जो हमसे पूछा जा रहा है रिगार्डिंग प्रोबेबिलिटी. यू गेट माय पॉइंट?
Yes, sir.
Your standard normal distribution is not representing the actual scenario. Please remember. एक्चुअल में तो आपका बेल शेप कर्व ही है. Standard normal distribution is just there or just present there to answer the questions that you put in to regarding probability levels. Just like now, with this understanding, if I want you that, okay, tell me, I'm just putting this question to all of you and you have to give me the the approach to solve that problem. My question is, tell me, if you have 100 observation and fairly removed, every outlier is removed, systematic error is removed, and everything is fine considering the case of random error, you have 100 such observation. Okay, tell me, what is the, or I would also repeat it like, how much observation will fall under mu plus minus 1 sigma? बताइए. या इस क्वेश्चन को ऐसे भी कर सकते हैं कि what will be the probability associated that your observation will fall between mu plus minus 1 sigma? बताइए इसको कैसे करेंगे आप. अगर आप इस क्वेश्चन को, जो भी लोग इस क्लास में हैं, if you attempt this problem and if you have understanding to solve this problem, you believe me that 50% of your doubts would be removed. Just listen to this question very carefully. You have to tell me, again I'm asking that, what will be the probability with which observation will fall between mu plus minus 1 sigma? अगर इसको दूसरे तरीके से बोले, जैसे भी मैंने राइट हैंड साइड बोला, लेफ्ट हैंड साइड बोले, what is the probability associated that your observation will fall between plus minus mu plus minus 1 sigma? अगर आप इसको अटेम्प्ट करिए जरा, सभी लोग, जो भी डाउट्स हैं वो आप बीच बीच में पूछते जाइए, हम क्लियर करेंगे. बट कैसे अटेम्प्ट करेंगे, क्योंकि अगर मैंने नेक्स्ट स्लाइड दिखा दी तो दैट वुड बी, योर एटीट्यूड टुवर्ड्स लर्निंग वुड चेंज. आपको अपना ब्रेन लगाने का मौका ही नहीं मिलेगा. क्वेश्चन इज वेरी सिंपल. आपके पास 100 ऑब्जर्वेशन है, ठीक है, यू हैव 100 ऑब्जर्वेशन. माय क्वेश्चन इज, व्हाट इज द प्रोबेबिलिटी विद व्हिच observation will fall between mu plus minus 1 sigma? ठीक है, let me just how, that's what I'm trying to.
सर प्रॉपर्टीज आपने बताया था, कैरेक्टरिस्टिक्स आपने बताया था.
अरे कैरेक्टरिस्टिक्स से नहीं, आपको प्रूफ करना है. नाउ यू आर इंजीनियर, यू हैव टू प्रूव इट. चलिए, अच्छा, मैं अगर 1 सिग्मा के लिए बताया हूं तो बताइए 2 सिग्मा के लिए. आपको स्क्रीन विजिबल है कि नहीं है? मेरे हिसाब से नहीं होगी.
नो सर.
जस्ट अ मोमेंट. अब बताइए, I have asked the how we are solving the problem. We are solving the problem like this: probability of x to have a less than value of x, yeah, or probability of x to fall between a and b would be. हम इसको सॉल्व करते हैं कि नहीं करते? So what is the probability that your observation will fall between mu minus sigma to mu plus sigma? देखिए, आप लोग क्या है ना, सुन रहे हैं, यही एक सबसे बड़ी प्रॉब्लम है. And I hate it that students are not in the class. आप लोग सिर्फ सुन रहे हैं. मैं देख नहीं रहा हूं कि आप लोग राइट लिख पा रहे हैं कि नहीं लिख पा रहे हैं. बट इफ यू डू नॉट राइट, you are good for nothing. इंजीनियर बन के निकलेंगे जिनको सिर्फ हवाई चीजें पता होंगी. The question I am asking, what is the probability that x will fall between a and b? What is the probability that your observation will fall between mu plus minus 1 sigma? So one arbitrary guess you made just like 68%. But what if I change the question? What will be the probability that your observation will fall between mu plus minus 2 sigma, mu plus minus 3 sigma, mu plus minus k sigma? How would you solve it?
हेलो सर.
बताइए. मैं आगे नहीं बढ़ूंगा, आपको बताना पड़ेगा पहले. हाँ बताइए
सर. हेलो.
I'm listening. Yeah.
सर, इसको हम सर कन्वर्ट करेंगे उसमें स्टैंडर्ड डेविएशन में और डिस्ट्रीब्यूशन फंक्शन.
कैसे कन्वर्ट करेंगे
सर?
कैसे?
म्यू प्लस माइनस 1 सिग्मा लिखा हुआ है, तो इसको पहले हम लिखेंगे म्यू प्लस माइनस सिग्मा, अरे प्लस सिग्मा माइनस म्यू अपॉन में सिग्मा, तो उससे वो जेड के टर्म में कन्वर्ट हो जाएगा, फिर हम टेबल से निकाल सकते हैं। हेलो
या प्लीज से अगेन।
सर, इसको हम जेड के टर्म में कन्वर्ट करेंगे, तो उसके लिए हमें इसको म्यू को माइनस करके अपॉन में सिग्मा करना पड़ेगा, जो हमारा ट्रांसफॉर्मेशन फैक्टर था एक, जेड इक्वल टू एक्स माइनस म्यू अपॉन सिग्मा। तो उससे ये कन्वर्ट हो जाएगा, ये -1 से +1 के बीच में रेंज के बीच में लाई करेगा। तो इससे हम निकाल सकते हैं प्रोबेबिलिटी ऑफ फंक्शन 1 माइनस -1, प्रोबेबिलिटी ऑफ -1। तो फिर हम जेड वाली टेबल देखेंगे और वहां से इसकी वैल्यू आ जाएगी 68.3।
ओके, लेट मी आस्क द अदर वन आल्सो। वैली शेट्टी, आप बताइए। वैली शेट्टी, आर यू लिसनिंग?
यस सर।
बताइए इस क्वेश्चन का आंसर। क्या हुआ भाई?
Sir, in standard normal distribution, if we replace the probability
Yes.
parameter values of A as mu minus sigma and B as mu plus sigma, then if we from the equations of
Mm-hmm.
so to get the final value, we should know the mean value and the standard deviation value, so that if the mu and sigma values are replaced in the equation, then we'll get to know the normal distribution functions and density functions with the help of the values from the table of exponential values.
Mm-hmm. You are partly correct, but yes, it is good that you have explained it. So basically, what we have to do, we have to replace the range which we are asking in terms of question. पारुल, आपको समझ में आए ये बात?
Yes sir.
So it is not just to remember everything. आपको ये भी देखना है कि how do we approach the problem, okay?
Sir, I have a query that every time we can't get
Yeah.
into the table to find the values of exponentials without calc in us.
Hmm?
To find a complete result of distribution functions and density functions of normal standardization, we should know the exponential values. How can we know without calc and the table if you can't see into the table?
No. It is not expected here in this course or in this domain that you have to you will be checked on your skills of how you are integrating a problem. No, that's not the case. That's why, fortunately, as I've told you in the first class, that fortunately in our domain, majority of the data set follow the normal distribution. And when some data is following normal distribution, standard normal distribution is almost applicable. We just have to find out the solution to our problem, not to complicate the problem. We do not have to check our integral calculus kind of understanding. Okay.
Okay.
Then there is a word called relative precision, and in relative precision we have to refer the ratio of the precision of a given measurement and the value of measurement itself. So it is the sigma d by d for a distance d is measured, and sigma d is the standard deviation. Then sigma d by d is called as the relative precision. Okay. And then if the dimensionless, it is dimensionless and often expressed as the functional ratio 1 by 10,000 or 1 by 50,000 ppm is frequently used with EDM instruments. So this is a very good figure you could see. High precision, low precision. You just take a look at this figure. So measures of precision, as I've told you, it has been the spread of the probability distribution of a measurement and or its random error component is an indication of the measurement precision. See, in this case, you have a bell-shaped curve, which is expressed in terms of your the so-called sigma, where the are observation lie between mu plus minus 1 sigma, 1.65 sigma, 1.96 sigma, and so on. And here the relationship between error and percentage area under the normal distribution curve is represented. And many times we have known that outlier would be detected by mu plus minus 29 sigma. Generally, in theory, it is written that the mu plus minus. Nowadays, people have changed this understanding, and a new concept of outlier detection has been arrived, and it has been seen that nowadays people don't follow this criteria anymore. Previously, in literature, you would also see that this criteria is written for outlier detection, mu plus minus 3.29 sigma. Where it would fall 3.29 sigma, 3.29 sigma fall between somewhere here. So it is considered that outliers post 3.29 sigma would be the observation from mu plus minus 3.29 sigma would be rejected. And here you could see the curve that's how the curve would be represented. So 1 sigma somewhere is coming here. So this is the 68.23. This is the 68.23. This is 1 sigma. Similarly, to the mu plus minus 3 sigma, almost 99.9 observations are covered. That's why it is written as 3.29 sigma as one possibility that outlier would be removed. But there are new statistics are coming out, and you have to follow the literature for that. I'll share that also. Okay. So from now onwards, this slide onwards, you would be familiar with this mu plus minus 1 sigma mu plus minus 2 sigma, mu plus minus 3 sigma, and associated probability standard. Okay, that's very important, that because you have to make those statements based on your probability concept. Okay, so obviously the mu plus minus 1 sigma is nothing that probability with um, probability at which the observation will fall between mu plus minus 1 sigma. So the percentage area under the curve and probability are related. Why? Because you have to answer it from the integral itself. Integral mu minus sigma mu plus sigma fx dx. This is your probability. If you kindly remember, how do you write probability? P fx, p x is equal x less than x, fx. How do you write it? You write like that. So area under the curve is another way of saying the probability. So probability with which the observation will fall between mu plus minus 1 sigma. Answer is 68.3, which you have just computed from with the help of a standard normal distribution. My next question: what is the probability associated with 1 plus minus 1.96 sigma? 95%. That will be computed based on your understanding of standard normal distribution. See, this is the example which we just discussed. The more how this 1 and 1 minus 1 and 1 has come up, that you have to again derive from writing. I'm just for one time, because some of the students do not follow the content. They just listen the audio, they just listen the video, and sometimes they feel very chaos, that how to write that p minus. So the p is arrived like this. When you have write z, that is x minus mu. So mu plus minus sigma. Oh, come on. Sorry, new version is not working anymore. I don't know what happened. Again, anyways, so you want to write mu minus sigma to, this is your range, and where you want mu plus sigma. So you have to replace x by that. So here you will minus mu upon sigma. Here you will minus mu upon Actually, there was some network issue. Campus network is some on failure right now. So I'm just sharing my screen. So that was the case where we have to answer the probability of standard error. Okay. Then the properties of the distribution. How do you write that probability z from minus t to t? That is obviously the t is nothing but from the table you can see it. That probability of mod z. How do you write minus t to t in terms of your basic function? That mod z would be less than t. That becomes nzt minus nz minus t. That these values you can take from the see from the tables, or you can also rewrite as 2 nzt considering the symmetry of the distribution. Considering the so-called symmetry of the distribution, you can write the 2 nzt minus 1. Okay. Just see in this slide if you have any issue. Similarly, we have 50% probable error. What is the way you can represent the two different problems? Initially, we have called about the linear standard error, which is this mu plus minus 1 sigma. We could also reframe the question by asking what is the 50% probability. That means this time I'm giving the probability, but I'm asking at what t you are, at what mu plus minus k sigma, the value of k I'm looking for. So in this, you could see from the question 50% probable error. That means we are putting the values of 0.50. Previous question was at what probability the value observation will fall between mu plus minus 1 sigma. Here I'm asking that what is the 50% probable error. That means I am asking about mu plus minus k sigma. What is the value of k for which the error would be 50% probable. So 2 nzt minus 1 is 0.5, nzt would be 1.5. Sorry, 2 nzt would be 1.5, nzt would be 0.7. From the table, you could see the value for 0.75 and you would get the answers. Okay. So there are two ways you can question. The previous was, I'm again, because why I'm repeating multiple times, some of you will probably get the point, but some of you are a little in dilemma what I'm trying to say. Please remember, either it could be framed like this. What is the probability with which your observation will fall between mu plus minus 1 sigma? There's one question. We have solved the previous one. There is another question, which is what is the 50% probable error or X% probable error? That means what could be the chance associated with your probability level, which is 0.5. So that is a way you have to explain it. So when you write from table, you could see there is nothing like 0.7 in your table. If it is either it is 0.7486 and then quickly jump to 0.7517, then you have to interpolate. Okay, then you see that the values are available. You just put in delta t upon 0.68. That means you are trying to identify how much I have to add from 0.67 so that we could achieve the 0.75. So obviously this function of delta t upon is very basic function of BTech first semester. The delta t upon t2 minus t1 is equal to the value of function available at 0.75 minus. So you write you add this much to your initial first point, then you will get the 0.6745 or 0.68, I would rather say, the 0.68 or simply the 68%. Sorry, not the 68%. In fact, it is the K which we are trying to identify. So it is mu plus minus 0.68. Come on, yeah. However, in the previous case, what was the sigma? Mu plus minus 1 sigma. So see, from 68.3% probability, you are down to 50%. So similarly, the sigma K sigma is also changed to a new value. So I hope you have seen this. If you have any doubt, you can ask. This is one example. You can answer it. We have a data set with a mean value 23.5 plus minus 1.367. This is always considered as sigma. Okay. So 50% of observation should be between 22.58 to 24.42 by following this principle. Mu plus minus 0.6745 sigma. This is the question which you have to answer. You take your time and answer this. That out of 77, 27 of 50 are between these values of 54%. It is why it is not exactly 54%? That you have to answer it. Which T function you are asking, Sumit?
सर 2 स्लाइड्स बैक पीछे वाले में हम लोगों ने भी देखा ना सर, लास्ट एंटी वाला फंक्शन जो आपने बताया अभी सर, वो it was resembling like that 5 function which we were doing yesterday.
हाँ सेम है, हाँ सेम है. It is same.
Yes sir. Okay sir.
Anyone who's capable of answering this? Why it is not exactly 50%? Any guesses? Alok, Sumit, Parul. Okay, anyways, take your time, come back. So this is the way you have to find out the, I'm just giving you 5-10 minutes. You just work on finding out the, as part of tutorial, the multiplier for these 5 cases. Practice it and give me the answer for multiplier of E90, that means 90% probable error, E95, 95% probable error, 99, 99% probable error, and similarly the others.